Okay, so so welcome again, and thank you all for joining today. It is with great pleasure that we welcome you to our online workshop on palm byproducts as a springboard to the circular bioeconomy of the future. So as all of you know, the Palmia family includes a wide variety of species. This includes date palm, coconut palm, oil, dome palm, and sugar palm, and several others. And they are considered the main source of livelihood to a big proportion of the world population. But unfortunately, their byproducts or secondary products are often regarded as agricultural waste, despite that they represent a sustainable material base for a wide spectrum of industries, ranging from compost, wood substitutes, pulp, and up to fiber reinforcements for advanced composites. And this workshop will highlight this great potential of these byproducts in the circular bioeconomy of the future. We have brought together world-renowned experts, and we will discuss with them what opportunities the palm byproducts have in store for us. We will also have the opportunity to interact with speakers and ask them questions about your research and your business. We would like to thank you again for your participation at the workshop, and we would also like to thank our speakers for their contribution. We are aware that many of you have had difficulties due to time zone differences and other work commitments, but thank you so much for attending, and we hope that you enjoy your participation. Okay, so let me turn on my camera. Okay, so we will start our workshop with a very special speaker and a very special talk. Our first talk will be presented by Professor Dr. Mohammad Jawaid from University of Putra, Malaysia. He will provide a talk about oil palm fibers and their numerous applications. Professor Jawaid, are you there?
Yes, Midani, I'm there.
Okay, so thank you so much for joining us today. So Professor Jawaid is a high flyer fellow from the Biocomposites Technology Lab at the Institute of Tropical Forestry and Forest Byproducts from the University of Putra, Malaysia. Okay, so I can see your screen. Okay, so now we can see your screen. So you can go ahead and start your presentation.
Thank you, Midani. Just a moment. I can just share the screen. Okay. Okay, good morning and assalamu alaikum to all of you. Basically, my name is Dr. Mohammad Jawaid, and today I'm going to talk around 30 minutes about the oil palm biomass and its various applications. And what we research, basically, we are going to cover that research we done on this oil palm fibers based composite and its applications towards the different applications. So before going into that one, I just want to give you the brief introductions about the UPM. UPM is one of the research-based university in Malaysia. We have 5 research-based universities. So we have one of the research university in Malaysia, and we are more focused on the agriculture-based. And we have a long history of that one, and we have faculties and postgraduate students from internationals around 80 countries we represent. And we have also participating into the different international standing of what called the ranking. And this is a little bit not updated. That one in 2021, our ranking little bit changed. And we have different faculties, and we have 15 faculties, and we have 11 institutes. So within that institute, there is one institute of tropical forestry and forest products. So I attach with that laboratory. And we have also a school, and our institute is also come under the higher education center of excellence, HICO. There is a few institute given by the ministry, and we have also different accreditation for different courses. And we have also collaborated from the few universities worldwide, and we have also MOU and MOA with different universities, and we have international students from the 80 countries, and we have also the summer school, and then we have also the research clusters, and we have also some commercial products, which I just show here to you. This is some transitional research and some awards, IP, and all these things are done. And also they have some community engagement project with Safe Kids and Air Asia, Farm Fresh. This is some of that one. So let's come about that, what we call that. He already given the introductions about me. So no need to go more on that. So this is my, what you call the research student, but most of them already pass out. I think 2-3 is left now. Most of them, the pass out, the PhD and master, they done from here. So basically I'm going to talk about the, what we call the, about the wild palm fibers and tree. I'm not going to take more because the other speaker is going to talk about the more on the wild palm trunks and all these things. So I will concentrate more on the fiber part. And then I will talk about the little bit research what the people have done on wild palm nanocellulose, wild palm fire retardant. And we develop some hybrid composites on the wild palm jute, wild palm kenaf, Kevlar wild palm. And there is a few applications and some projects we already done on the wild palm base. So if you look overall the scenario of the wild palm tree, there is a 42 countries cultivating the wild palms in around 27 million hectares. And Malaysia, Indonesia, and Thailand, basically the Malaysia and Indonesia is more producing the wild palm, and they are dependent on the palm oil on the revenue generations and all these things. And the wild palm tree, I don't need to go more on that one. If you look onto the distribution of wild palm plantations worldwide, there are several countries they are doing that one. And distribution of wild palm plantation in Malaysia in different states, you can find out it. And basically when we are looking into the, what we call that's the wild palm. So basically there are 3 things we can use from that one: wild palm front, and empty fruit bunch fiber, and wild palm trunk. But most of the time the empty fruit bunch is more readily available, and because that the palm oil mill use the extracted the palm oil, and after that they dispose it, and it's a one of the hazard materials. So there are a lot of industry nowadays, they can clean up and they can make the fibers, and you can buy the fibers and use for the different purpose. So if you look into the wild palm conditions, that one, there are thousands, the million tons it's coming out, and then the remaining biomass, it's very difficult. And one of the problem for the palm oil mill to how they are going to dispose it, that one. So the wild palm biomass can create substantial environmental problem when supply left on the plantation field. And if you look into the palm oil industry, if you look into that one, the palm oil is 10% and the 90% is a biomass, And when you look into the biomass, it wild palm fibers, wild palm fronts, and wild palm trunk fibers. And this is the things, what we call that it's coming out as a byproduct from this industry. And if you look into the, what we call the wild palm waste, that one, the mesocarp fiber, the palm shells, empty fruit bunch, and there are trunks and fronts are there. Generation of the wild palm waste during processing, and their amount in the million tons, like 30 million tons amounts, and it can vary from that one. When we look into the chemical compositions of the wild palm biomass, we find that this have a good amount of cellulose, lignins, and other material, which can be suitable for the other applications. For any form of strength or what we want, we can get it. So you look into the comparative, and it can be vary from the place to place. And this data, because of that, you saw that the value we return into the range, that one, because some people have reported the 40 and some reported 50. So we take the range of that one. So when you took the range, so this oil palm have a good amount of the cellulose, which is giving the strength to for a construction or any purpose. And they have also the lignin content is better. And they have also the tough fiber. So when we look into because nowadays everybody's are talking about the nanofillers, what we call that, the oil palm. So there are few researchers already, previous time we already done on that one. This is a very old data that first I done at that time. The very few people are working on the oil palm nanocellulose when we started in 2014. That time we done the microcrystalline cellulose from and just we done the total chlorine-free pulping using acid hydrolysis method, and then we can use the hydrogen peroxide bleaching sequence for that. And we done the FTIR on that one, and we find out that acid hydrolysis does not affect the chemical structure of the cellulosic fragment. And then we done the morphological part, and we find out that our MCC was investigations using by the scanning electron microscope. And also we done the AFM from that. This all the things are published work you can find into the literature, that one. And we also done the XRD, and we find out that the MCC have what we call the crystallinity is 87%. And then we also done the thermal properties of that one, and we find that the degradations of the temperatures for the MCC and pulping and residual content, and how the peak temperatures we are getting. In view of the thermal analysis result, and concluded that MCC samples produced from the oil palm pulp has good thermal stability, it can be suitable for the production of the green composites. And we also done the microcrystalline cellulose and what you call, we also done the cellulose nanoviscous from the MCC, and we analyze it and compare with the MCC. This all the things which you can search into that one. It's already published in Carbohydrate Polymers Journal long ago. And what we call that the structures and morphological structure, we also analyze, and we find that the size is within the range. And we also done the what we call that the XRD of that one, and we find out the crystallinity of that nanoviscous is 88%. And we also analyze the TGA of and then we find out that the produced cellulose nanoviscous exhibited better thermal properties than the MCC, making them suitable as a reinforcing agent in the biocomposites preparations. And we also done another research, we call it the oil palm fire retardant. So we modified the oil palm fillers, and we make the powder from it, and then after that we treat it, and later on we make the composites and all this from that one. So basically that how we treated that. First we did the grinding of the oil palm fibers. We done the chemical treatment by bromine waters and SnCl2 and cryogenic crushings to make it the very fine powders, followed by the high energy ball mill process. And high energy ball mill process proved to be sophisticated technique for the reductions of the macromolecules. This is a physical method of making the nanomaterials. And we check the size, and then the what you call through the TEM stage, TEM image, and we find out that lowest size we get the 6 nanomaterials, but there is a range of the size we get after the crushing. It may be 40 nanometers, 60 nanometers. There are different range out there. So because of that, we plotted the number of particles in that TEM image. And we also done the XRD of that nanofillers, and we find out that the decrease in the crystallinity indicated that the mechanical operated ball milling induced a significant decrease in the particle size from the raw material to the nano oil palm fillers. And we also analyzed that the untreated oil palm fiber brominated and the brominated with the tin chlorides, we done it that one, and we find out that from the analysis, all the FTR spectra can be confirmed that the SB, the materials SB we call is that which have a bromine and tin chloride, both we treated with that one, and containing the element, we find out that in that element, the SnCl and bromines are there, absorbed onto the surface of the fibers, while it's still maintaining the basic structure component of the cellulose, hemicellulose, or lignin. So it did not disturb that when we are treating these fibers, it did not disturb the structure of the fibers. And we, what we call that, we saw that after that, the before and after, we look into the left side, we look into the comparisons of that, before ball mill and after ball mill. And we investigated that the EDX and showing the presence of tin, carbon, oxygen, chlorine, and bromine element, both before and after the ball mill. And we also done the TGA and DSC of these materials, and we find out that the result nanofiller can be used for the fabrication of nanocomposites with improved fire retardancy, and this can be incorporated as fire retardant nanofillers in different polymer matrix to fabricate the nanocomposite for distinguished industrial application. We also earlier done on the oil palm jute fibers, because the oil palm have coming from the fruits part and the jute is from the bast fiber. So we have a purpose to make the unique composite that can be used for the advanced application. So we done the different layering patterns of the top oil palm, both side, and then the core we put in what you call as the jute fibers, and the both side we outers, both side layers we put into the jute fibers, and we make into the composite forms, and we studied the different properties of its mechanical properties and its what we call the other properties. And we find out that the woven fibers in the PORE become enhance the tensile and flexural properties of the hybrid composite as compared to the pure EFB composites. And we look into that one, the composite which have what we call that the jute fiber have better interaction bonding with the matrix compared to the only EFB with the epoxy. And we also done the dynamic mechanical analysis of these materials, and we find out that one, the EFB and jute hybrid composite exhibit the lowest storage modulus, and it shows that increase in jute fiber loading enhance the stress transfer molding. I just want to explain something. The DMA is that process. It's a form of a testing in that you measure the mechanical property with the temperatures. And in that you get the storage modulus, the of the materials, you can get the loss modulus, and you can get the tan delta, that is the damping factors of that materials. And we done the loss modulus. So we find out that increased trend in loss modulus upon increasing the jute fiber content, because the jute fiber have better strength. And we find out slightly decrease in the rubbery stage, and the TG obtained from the loss modulus found to be lower than that one. And we look into the damping factor. So you saw that the black one, the EFB is higher peak because they have a less strength and they have a less interaction between the matrix and the fibers. So the peak is higher in height is lower in jute fibers and hybrid compared to it, which shows that lower damping and good fiber matrix additions on it. And there is another plot. You can draw the plot. It's called the Cole plots. You can plot, and through that plot, you can get the information that your material is heterogeneous or your material is homogeneous. So we find out that in the form of Cole plots, we find that irregular to imperfect semicircular to an irregular shape. We find out, so it's indicated that our materials heterogeneity among the EFB jutes and hybrid composites are there. And we also done on the Kenaf oil palm. There is one research we done on that one. And in this research, what we done that one, basically, we want to look the effect of the radiation on that. So just I'm going, this is the simple that one. And then after that, we done another research on the Kevlar and oil palm. In that, we look the radiation effect on that one. So there is one student, she is working on the Nuclear Malaysia Agency. So she helped us to, she have access to the Nuclear Malaysia Agency. So we go through the eradicated into the gamma cells using the different dose of that, the radiation dose. And we find out that the radiation dose is just taking you to the, this is the water absorption is improved, and the interaction between the fiber and matrix also improve after doing the radiations to that composite, and compression strength also improve. And this is showing that, like, for example, 50 and 100 show better compared to the non-irradiated and the 25. And we also work and about to finish the 1:1 PhD on the oil palm and sugar farm. We are developing the insulation board. And our purpose to use this both waste materials, that sugar palm is also a waste materials, and the oil palm both is a waste materials. We already done the treatment of this one. We make the different types of the insulation board by using a different what call that the compositions of the fibers ratio and all these things. And we studied the thermal properties, acoustic properties, and all these things. And we find out this is a very suitable materials for insulation. We already published some works on that one. So you can find out that work on the construction and building materials. We published 2 papers related to this one. And we done this analysis. All analysis is almost, it's the output from this research is published into the journals. And when we look into the overall scenario, that one, it can be used in automotive, it can be used in aircraft, and it can be used in the decoration, it can be used in furniture, it can be used in building and food packaging. But I'm just going to take one project recently, international project, which we completed on the food packaging. So I just going to take briefly on that one. We done the packaging material from oil palm EFB, and we have the previously project we started in 2016 with Malaysia and UK partners, industrial and academic partners, and we finished this project in 2019. So basically in this project, our purpose to use is agro-waste materials and use of the new concept of active packaging, and we have to develop that type of packaging material which can be reduce the pathogenic microbial growth, increase shelf life of the packaged food, and reduce the food loss, reduce the food loss across the supply chain, and making it contribute to minimize the waste to the landfill problem. So look the concept, this is a fiber, then you do the pulping. This is a simple what called the flow for this one. And we have, why we chooses this one, because it's cheap and large in quantity, continuous supply from waste to high value added product, low lignin content and high fiber and good bonding strength are there. And it can be replaced, can be used as a packaging paper bag and fabrication of cartoon, food tray, vegetable tray, and environmental friendly, non-toxic, biodegradable, that one. And this is a pulping plants. You can do the pulp molding by wet type. You can do the pulp molding by the dry method. So this is the setup of that industry where we done the pulping. So this is the pulp we develop into our institute, and this pulp we taken into that industry and we put into the pulverizer tank. And this pulverizer tank, you can, if you want to make any additives and anything, you can add it that stage in the pulverizer tank. And after that, you saw that putting the pulp here, high speed agitations are there, low speed agitations are there. And we pour after that, pulp slurry was pumped into the holding and mixed tank. And mixed tank, after that, there is a pulp mold is there and there is a panel. So you can control everything, you make the setting there. And that setting, accordingly, that type of product you are going to produce on the base of the mold you feed there. So we produce this lunch box from that, and we look into that one. There is a positive effect, there is a smooth and well formed, and there is a positive charge, easy bonding with the waters and oil repellent agent. And we done the second stage trial in around 3 years. And in this trial, we make what we call that we make the plate, because that time they have already doing. And this is parallelly, we are also doing the research in the UK. So initially they also try to make the pulp molding products by using a oil palm fiber, which we sent from the Malaysia to them, but they are unable to produce the right shape. So then we visited to the UK, and I and Mr. Amir from the pulp molding company, we visited to the UK and we looked the problem with them, and then we shot out the problem. We designed the new mold, design feature for them. And then after that, this is one video there. If just I play for a moment. So this is basically a pulp molding machine, and it can be taking that one. And then we also done the life cycle assessment of the pulp molding process, and we also look into the outcome from this product. Is it this pulp mold, means how much the energy consumption on every step. And we also try to pack it into the professional way compared to the plastic, what the current hypermarket is using. And then we also design it. We done the leading of this, what called the pulp molded tray, and we use the biofilm, and you use the bioadhesive. So it's 100% biodegradable and compostable tray are there. So this is the film we use for tray sealing by a UK company. And then we also put the different types of the fruits and other things and look into the professional way how we are going. And then we will study that in original packing and what the weight losses happen into the, this one. So we studied this one. Also, we studied the meat, and we look into the coated tray and the coated tray with the chicken to look into the contaminations and all these things. We use the pad to find out the solutions, and no packing failure was identified over the testing method. And also we do the consumer study in the Tesco UK, and we ask them the question, how acceptable or unacceptable do you find the sample as a ready meal package? So the 42% of customers found that plastic packaging acceptable as produce packaging, but 27% found it neither acceptable, non-acceptable, that one. But 85% customer have agreed that this is a very suitable, safe bio pack product. And we also look into the disagree on packaging. So 95% of customer agree that the safe biopack serve its purpose and produce packaging. And we also ask them agree or disagree with packaging, believe the produce inside with good quality. So 57% customer perceive that is to contain a good quality product. And we distribute
can I ask you to wrap up, to leave?
Yes, about to wrap. Don't worry that.
Just a couple of minutes after you finish to answer any questions, because I'm sure we will have a lot of
just
questions.
2-3 minutes, Midani. Don't worry that. It's long, but I'm going to wrap it too.
No, it's very
So is the key finding, we find out that the wild palm is a suitable material for packaging, and then it can have enhanced additives, and pulp molding can be used for fresh products, lamination, fresh meats, and antimicrobial laminations. And we also done through the injection molding also, which we make by using a wild palm with the biofiller. We make the sheets by using that one, and that sheets can be we analyze the properties of that sheets, and we look the strength and properties and all these things, that one. And we done the trial production of packaging tray. We done the vacuum forming machines, and we also use the industrial vacuum forming machines to produce. So you looked at we form the vacuum form tray by using a wild palm and biopolymers. We also done the hot press by using that one, the productions of the tray. And also what we call we make the meat tray, because we given that one, because the meat is going to touch with the tray. So we given the strip here, and we look that you look the back and everything is very smooth. And if look other just a small application, automotive, there is also application. You can wild palm waste, and you can make into this is a very old information from the proton. So I don't know existing, they are using it or not. And there is a similar with that, our research, we have a plan to develop the wall construction by using a hybrid materials, which we develop by using a wild palm, and that one. You can also use the wild palm in the furnitures. You can also use wild palm into the aircraft application, several types of aircraft random. Somebody have made it, and they compare with the bamboo, banana, kenaf, and others materials. And we concluded from this this is the wild palm biomass receive high concentration and one of the most viable alternative source of reinforcement in composite materials. And this can be reinforced with the thermoset or thermoplastic. Any materials can be used to make by using the wild palm waste. And this wild palm fiber, trunk fiber, front fibers, and powders fibers within that one show effective and considerable improvement in the mechanical and thermal properties. And the wild palm fiber-based composites can be effectively utilized in automotive, aircraft, and construction materials. And I also recently, I joined one of the journals as a chief executive editors. I have a Partanika. So I invite all of you, the participant, please go through the website of Partanika journals and submit the papers to our journal. We have 3 journals on science and technology. We have a tropical agriculture and we have social science aspect of that. So lastly, I acknowledge all my co-researcher, PhD students, and UK and Malaysian industrial and academic project partners for supporting our research project. And thank you so much for all the listeners. And this is my email ID. If you have any query and anything, you can email further after that. Midani, finish. Thank you.
Yes, great job. Just on time. Thank you so much. So you want to stop sharing the screen? So
yeah.
if any of you have questions to Dr. Jawaid,
you can if you want
please
to
type
ask
it in the chat box. So we have a question so far. Dr. Adham Said was asking if he was wondering about the water resistance of those plates, the molded plates.
Yeah, that one, what we have to do generally, because it's the we use the water resistant agent to mix it, that one. So make it water repellent. That we are doing that one. We are adding the water repellent, oil repellent also. We are adding in that. So according to the price, the price value, that if they do not bother about the water resistant and all these things, then we don't add it. But if you want it, they can add into that one, because the extra charges is there to the product.
Okay, so another question from Dr. Manoj Kumar Singhi. He was asking if the fire retardant in case of fiber, but what about the polymers used? Can you please highlight this?
Yeah, basically this is the first part of the research. Basically from this fiber, frankly, I don't say it's a fire retardant or not, because we tested the fire retardant properties at the fiber stage. So basically further, we already tested by using, we work on the, what we call the epoxy resins, and then we make the composites. First we put the this filler into the epoxy matrix, and we find out the right formulation, that one for further making, because we use 1%, 3% and 5%. And that time we tested the fire retardant properties of UL94 and LOI. We done it that one, and we find out that one, this is have a fire retardant properties. And further we make the hybrid composites by using optimum formulations, and also we compare with the nano clay and MMT, which is commercially available, and we find out that our fire retardant materials have a comparable property with the commercial. This all the things already published. You can find into the my papers, that all already published this one.
Thank you so much. So another question was about how good is the vibration damping for those composite made from oil palm fibers?
Vibration, basically vibration we done one time with one student, but means that on the properties is not bad, but means we are unable to publish that work still, but we done the vibration testing. The acoustic property is very good. Acoustic, we done it that one, but the vibration, we tested it that one, but unfortunately that we do not formulate into the, what call that, the paper-wise, because that we done the testing in another place. We have no facility, and later on we published. So we only left the vibration, So we don't publish that work. But there is a not bad properties. That the properties is okay. That
So we have one last question before we proceed to the next speaker. So Dr. P.C. Vangaya, he was asking about the cost. Are these moldable plates cheaper than the plastic ones?
Yeah, basically that the cost is higher than the existing plastic materials, because it's that one. But what we call that one, as the industrial partners say, if the bulk production, they get the more order, they can be more, the gap between the plastic price and this price will little bit minimize, But of course, it's costly than the plastic. We cannot compare the plastic price with the pulp molded products, It still is costly.
Yes, I understand. Okay, thank you so much. So there are still few other questions, and if any of the audience still have other questions to Professor
I will try,
Jawaid,
Midani, don't worry. That chat, I saw some questions, so I will try
please
to reply.
chat with Dr. Jawaid in the chat box. So,
I will try to reply.
so now we have another excellent talk from Germany and Malaysia, a joint presentation. So it's titled Future Potential of Palm Trunk Fibers in Supplementing Timber, Quantities, Techniques, Challenges, and Opportunities. So this will be presented by Professor Dr. Arno Fruehwald, Emeritus Professor from University of Hamburg and Executive Partner at Palmwood R+D, as well as Professor Katja Fruehwald-Koenig, who is a professor at the Technical University Ostwestfalen-Lippe. I'm sorry, I'm not good at German, as well as Dr. Yueh Feng from the Malaysian Timber Board industry. So Dr. Katja, will you be sharing the screen? Oh, you already started sharing the screen. Okay, so, so let me unpin Dr. Jawaid.
Yeah.
Okay, so so who will start? Is it Professor Arno?
I will start. Yes.
Okay.
Thank you, Mr. Chairman. Can you hear me all?
Yes.
I hope so.
Yes, Prof. Yes, we are listening.
Thank you, and greetings to Malaysia. Thank you. I will start with the presentation. Katja will be the master behind us, and Dr. Loh will do some talks on plywood from oil palm trunks. So we would like to take you in the world of palm trunks, not dealing with other palm fibers, but only with trunks fibers and trunk material. And so the fact is that palms are trees, or certainly have the form of trees, but they are monocotyledones, which is a big difference to the dicotyledones, which are the common trees. Palms grow very fast, so the biomass production is very high, at least as double or 3 times as high as other timbers, with 5 to 15 tons of dry material per year in hectare. And the fibers can be used as a byproduct of fruits. So palms normally are grown for the fruit production, not for the fiber production. So worldwide, we see about close to 50 million hectares stocked with palms, different types of palms, several hundred species, and having or producing between 400 and 500 million tons, dry tons of fiber material. And about 30% of that fiber material can be found in trunks. So the next slide, please. And so we see, if we look to the 3 most important palms in terms of trunk material. So we see oil palms, coconut palms, and date palms. You see the estimated area, 25 million hectares for oil palms, and there's quite a short rotation period of up to 30 years. And the estimated trunk volume per year available from these 25 million hectares is about 150 million cubic meters per year worldwide. And at least 2/3, even more than that, are in Asia, Southeast Asia. Coconut palm live longer, so they have a rotation period of up to 80 years. And the estimated volume is smaller because also the estimated area is smaller. And date palm are grown on 2.5 million hectares roughly. And their lifetime is even longer than that. And so the estimated trunk volume available per year is even less. So, but all, if we consider all, including the other palms, we have at least more than 200 million cubic meters of palm trunk material available per year, compared to 2 billion commercial timber for uses is about 10% of the timber volume worldwide. So the next slide shows us the potential to supplement or even to substitute tropical timber species. So if we concentrate on Southeast Asia, have a look to Indonesia, for example. The total harvested volume, according to FAO in 2018, total harvested volume of tropical timber, hardwood timber, is 74 million cubic meters. If we deduct the forest plantation, then it's 61. And if we look to the potential of oil palm trunks in Indonesia, which is only 50%, roughly 50% of the total volume, then we have between 50 and 75 million cubic meter potential per year, which is almost similar as to the harvested tropical hardwoods. And then Indonesia has also quite a lot of coconut trees. So we have another 10 to 12 million potential. The same is with Malaysia. If you look to Malaysia, the potential for oil palm trunks, they have mainly oil palms, not so many coconut palms. It is almost double the potential compared to the harvested commercial timbers. Thailand is a bit different because their oil palm plantations are not so large, but still it is remarkable. And the Philippines, they have almost no tropical harvesting. They have only plantations. They have quite a lot of coconut potential. So we see from these figures, the potentials in Southeast Asia are as high as the annual cut. And if you consider that the cuttings of tropical timber species are going down during the next years, even more than today, then really there is a big challenge to use these coconut. And if we compare the forest plantations, if we sum up the forest plantations and sum up the area of palms in Asia, we have about the similar 30 million hectares, and the productivity with a fast-growing species like the light-colored, lightweight Sengon in Indonesia, for example. So the productivity of oil palm or coconut palm is almost the same. So both the palms and the fast-growing forest plantations grow on former tropical land, forest land. So it is almost the same, should be the same in the discussion. The next slide shows us the public perception. If the public looks to palms, and if they look to coconut palms, they feel very well. They have a very good feeling because coconuts are a very exotic food, and instantly they think on beaches and on holidays. If they look on date palms, they also, the first which comes in mind is the exotic food, the dates. And then they realize, okay, the date palms are isolated spots in a desert. This is good for nature. So date palms are also accepted very well. If they look to oil palms, they instantly have a bad feeling because oil palms destroy natural tropical forests. They think about these very nicely looking young orangutans. They think on biodiversity. They think on climate change and all these things. And they think, especially in Europe, they think palm oil, okay, it is important, but it can be replaced. But all the other alternatives are much less productive. So they really neglect the economic and the social aspects in the oil-producing countries. And as I said, the palms grow in the same location as the fast-growing planted species in the tropics. So it is really a pity that if people and even the timber industry looks to palms, they see only the fruits, not the fibers. And so we have to make aware that palms are producing fruits and fibers. The next slide shows us goes a little bit deeper in the productivity and in the potential value. So if we concentrate on oil palm, at the moment, oil palm trees, or oil palms, then during the lifetime of 25 years and per hectare, we get about 100 tons of palm oil. And the 100 tons have a value, economic value, the crude palm oil, between 50 and 60,000 US dollars. The empty fruit bunches, we just learned it from the former presentation, have no commercial value at the moment. The palm fronds hardly have a commercial value yet, maybe in future. The biomass below ground has no commercial value yet. Only the oil palm trunk has some commercial value, and if you would take 50 tons of products from the plantation, then we could generate a $10,000 value for the semi-finished products. For the finished products like furniture or building components, it would be between 20 and 30,000. And if we would calculate the value, for example, as a fertilizer from the empty fruit bunches, or from the fronds and from the below biomass ground, then and even produce some products from these fiber materials, then we easily could come up to $60,000 per hectare economic value over the lifetime. So we have a balance in economic value between the oil and the fibers, if we do it well. Next slide shows us the comparison between oil palm, coconut palm, and date palm. So I'll come more to the processing now. So we see the oil palm have quite a short lifetime, with 25 to 30 years. The trunks are about 12 meters in length. The coconut palms are double as long, up to 24 meters. The date palms have about 15 meters. So the most important things are the density of the timber. The average in oil palm is 0.3, roughly 0.3. In a coconut, roughly 0.5 to 0.6, and in date palm, 0.5. And from this, the moisture content in the oil palm is very high because the density is low. And in the coconut palm, the moisture content is lower because the density is high. So the reason for this very different density, you see the variation for the oil palm between 0.1 and 0.7. The same is with coconut palm, but it is not the same as date palm. It's the age, mainly the age of the palm. The date palm is quite old, so the palm is still alive all the time in all parts of the trunk. And so it grows thicker to thicker cell walls with the time. And if the palm is older, the cell walls of the parenchyma cells are thicker, and so the density is more uniform and the density is higher. Therefore, coconut palms have quite high density. The date palms are quite uniform in density. So this is a big challenge, this density and moisture problem. So the next slide shows us one example. You see on the left, you see a disc from an oil palm trunk. You see the very dark color in the outer part, the high density, mainly caused by thicker cell walls and by more vascular bundles. Vascular bundles are fibers which have a high density, a density of up to 1.4. So as the numbers of vascular bundles are increasing, the density increases, the strength properties are increasing. And the diagram shows us the development of the density across the diameter or along the diameter of a palm trunk, with about 500 kilograms per cubic meter in the outer side and about 200 kilograms in the inner part. So this is a challenge for processing. This is a challenge for product development. Next slide gives us an introduction in the properties, in density, in MOE, MOR, and so on. I don't want to go in detail. The only, if we compare on the very right column, the pine and spruce properties with the palm wood properties, we see if we go into the higher densities, medium and higher densities, we have similar properties compared to pine or spruce. So this gives us the information that we can use the palm wood in very different products. This is a chance, but also a challenge. And we can use it even instead of softwood species like palm and spruce, if we do it well. And so this is the challenge for us as researchers to do it well and for the industry to do it well. So next slide gives us a view on the complexity of the structure. So we see the more yellow material. This is the parenchyma. These are the parenchyma cells, thin walls, very big lumina. They contain the water. So oil palms and other palms need a lot of water to store the water for the dry season and store also a lot of sugars and starch also for the dry season. And we see the dark spots. These are the vascular bundles with the fiber caps, high density. Density I mentioned already between 0.8 and 1.4, whereas the density of the parenchyma is as low as 0.05 grams per cubic centimeter. So this is a big challenge for the machining. So this is like a reinforced soft plastic material, fiber reinforced soft plastic material, a challenge for drying, big challenge for drying, and also for machining and for grading and strength related design. So we have to do good grading of the material as well. Next slide gives some relationship between the properties on the left side and the challenges for the processes on the right side. So this means that density distribution, we need a product mix to use the whole trunk. The high moisture forces us to develop special drying techniques and to avoid defects in drying. The high sugar content and starch content and the high ash and silica, high ash and high silica is because of the high amounts of water taken up from the soil and all the elements are taken up. So this is a problem on the one hand to avoid mold and fungi and insects. Insects are attracted by the sugar. And the ash and the silica takes us to develop new tools and new tool materials. And the complex structure, as I said, is a challenge for the processing and for the, especially also for the product design. If you look, for example, to tension strengths compared to shear strengths, this is a very, very big difference between tension strength and shear strength, much bigger than in normal timber. So product design is a challenge in that case. Next slide gives us how we can manage this. So the density variation can be managed, partly managed by appropriate sawing pattern and by good grading and sorting. The sugar and starch problem by temporary treatment, for example, after sawing, then temporary treatment, for example, with acetic acid before drying, the ash and silicon with the new tool materials, and the high and low and medium density. We can use the material in different parts of a product, in a composite type product, or we can grade the material and put it into different products. So the next slides gives us some ideas about the product. So we have first the possibilities we can produce products. If we look, for example, oil palm are a very universal material if we do it right. So with the grading, with the proper machining and so on. The coconut palm are quite heavy. The material is quite heavy, the density is high. So for blockboard and for plywood, it is hard to process. And the date palm is also very good for almost all different type of timber-based products. Next slide gives us the pictures. So an example for lightweight blockboard material. So this is palm wood core material with a density of something around 0.2 veneer overlaid. Next slide gives us a flash door panel, also with a core from light or medium weight blockboard, whatever sound insulation we need, for example, whatever strength we need. We can use lightweight or medium weight or even heavyweight material. Next slide shows us a 3-layer solid wood panel, CLT, which was produced in industrial style. Next slide gives us a beam, laminated beam, glulam, produced from oil palm. And the next slide brings us to Bali. This is a newly built conference center at Hyatt Regency in Bali, exclusively built from coconut wood. Very nice, and this is a recommendation to have one time a Biopalma conference at Hyatt Regency in Bali, which is a very nice location, which makes good feelings about palms, because the beach with coconut palms is only 50 meters away from this picture. Okay, next. So some examples for plywood. On the left, we have a package of plywood as door core material, flash door core material, and you see 2 examples using plywood for furniture. So the next slide, examples for the processing is sawmilling and drying and sorting for sawn timber, then is board manufacturing, beam type, construction elements, and veneer plywood. So these are the main processes. And here we see the process flow. If we have, for example, 2,000 hectares of harvesting area for oil palm, we get 140,000 cubic meters and we can produce lumber. And you see the recovery rates, 60% to 65% after sawing. And then we have the drying, we have the grading, and even the planing afterwards for smooth surfaces. And we get after planing or after drying and grading, we get about 50% recovery rate, which is as high as common hardwoods, even higher than tropical hardwood timbers. Next slide is the same for the production of glued laminated timber. We have the sawing, and then it's a very similar process to, for example, softwood uses for glued laminated timber with the adapted process steps, of course. Okay, next. So if we look to the results, we have achieved for all the main process steps, very good results. So for material management, for sawing, for drying, for the planning, for the visual and even strength grading, for residues management, including energy or fertilizer, and for complete mill design, mill setup and investment production costs, and with really high recovery rates for the products. When I say we, then I mean 2 very big projects. One big project is Palmwood Net, and Dr. Henniken was what is called the chairman of this project. Dr. Henniken is among the participants. So these industry partners, it was a consortium of 5 German industry partners, Möhringer Leitsminda, Jawaid, and Palmwood R&D, and then from Malaysia, Frim, FIDEC, MTIB, and from Thailand, Kasetsat University, and about 10 more partners. So they did a lot of research on oil palm trunk utilization during the last, let's say, 10 years, and achieved really good success. So the next is plywood, and I would like to give the floor to our colleague, Dr. Loh from Malaysia. Dr. Loh. Hey, Dr. Loh, can you hear me?
can you unmute yourself? Yes, we can see you, but can you unmute yourself?
Yeah.
Okay, so Dr. Lu, can you unmute yourself, please? Okay, so you're unable, I'm sorry. So can you try now? I'm sorry, I didn't realize that you were unable to. Can you try to unmute now?
Yeah.
Sorry about that.
Okay, thank you very much, Professor Arno, and also Professor Katja to invite me to join their presentation for the workshop today. So basically, I will talk more about the plywood manufacturing using the oil palm trunk. So basically in Malaysia, mostly the plywood industry use tropical timber and some of the rubber for plywood manufacture. But since the year 2006, few industry have to try to make plywood from oil palm trunk due to shortage of the timber supply and also high cost for the timber logs from the forest, and also some have to use small diameter logs from plantation like rubber. Now we only have 3 successful mills already produce this OPT, oil palm trunk plywood, about 50,000 meter cubic per year, and have been commercialized local and also export to few market international. The OPT plywood mainly for the construction is for the as a concrete formwork for the construction material, door core materials, and also used for the utility or general use. But lately, we also try to use it for the furniture making in various thickness, like 3 mm to 50 mm the thick thickness of the plywood. Okay, next. The OPT plywood manufacturing process is the same compared to the conventional plywood process, just like the normal process of the plywood. And also you can see that from the flow chart, the process chart, you can see for the law yard, peeling, drying process, gluing, pressing, and also finishing. Then you can market it as usual. Based on the natural characteristics of oil palm wood, such as the rough surface, high moisture content, density variation, as I mentioned by Professor Arno before, the industry need to do some modification and enhancement on the process. So we have done some work previously, like plywood quality enhancement with resin treatment or resin impregnation. And also we also have done some process and machinery upgrade for the dewatering in order to get a shortened time of the drying process. Pillar with some segregation, pre-drying chamber, Breton roller press on the drying process, and lattice on the densification chemical treatment to strict the furniture requirement. Okay, next. So look at the slide. We also have calculated the production cost for the normal OPT plywood and also plywood with some modification process back to the year 2014. As shown in the graph, you can see that the major cost is from the raw material and the wages, about 30% and 27%. The production cost shown in table, normal OPT plywood is about $310 per meter cubic. And with resin treatment, the cost will be higher due to the chemical cost and roughly increase about 10% to the production cost, but the cost can be reduced when we do some modification on the dewatering process. And also we can do some saving on the drying process. Okay, on the next slide. I would like to summarize that the oil palm trunk can be used to produce a good quality of plywood with a suitable modification and also some of the enhancement process to the existing technology or machinery in the mill. The OPT logs can be stored longer with a simple treatment. The pillar need to be modified to peel the soft inner part. We also can, now we can peel deep vinyl, only deep vinyl up to 6 millimeter or maybe more, but not very thin as is now. So basically, the crucial part on the drying process, a lot of work have been done by the researcher in Malaysia to shorten the drying time and also increase the quality of the vinyl, as well increase the capacity on the mill. So the rough vinyl surface also the main issue during the gluing process because it's consumed more glue, but less glue consumption if the vinyl we undergo the pattern press drying process due to the densification. The final, the others problem on the vinyl handling and also the uneven thickness of the plywood due to the density variation as mentioned before. So hopefully with all this modification on the processing and also do some enhancement, I believe that the OPT plywood can be compete with other plywood from the hardwood and also the softwood in terms of quality and also is from the sustainable resources. So not only plywood so far, we NTIB under Malaysia Timber Industry Board also are working closely with Professor Arno and also Professor Katja from Germany on the oil palm timber now. So with that, I conclude my slide here and to be continued by Professor Arno. Thank you very much.
Okay, thank you, Dr. Loh. So I would like just to take one slide for the for some aspects of economics. We intended to say something about the ecological aspects of trunk utilization, but due to the time, we invite you to join the meeting in September. Most likely we'll have a special lecture on ecological aspects of palm fiber utilization. So just one remark here, an example for the economic values. So if we take a 40,000 hectares plantation area, so we get continuously about 120,000 cubic meters of oil palm trunk from this area. So the transportation distance is very short. This is a very big advantage for oil palms. And from the 120,000, we get about 60,000 cubic meters of dry lumber. We can produce building products, furniture components, 3-layer panels, 1-layer panels, about 40,000 cubic meters. And if we look to the value generated, this is about at least $250 per cubic meter. And we have a job creation of about 1,200 jobs from the 120,000 cubic meter of OPT. This makes about 1 job per 100 cubic meter OPT processed, which is quite similar to very many industrialized countries. In Germany, for example, we have the same ratio, 1 job per 100 cubic meter of harvested groundwood. So with that, I invite you to the presentations in September, but Dr. Midani will do it at the end of the workshop today. And I thank you for the interest. If you have questions, you can put it now or you can put it later using these email addresses. Thank you.
Okay. Thank you so much, Professor Fruehwald, for this insightful and eye-opening talk on the utilization of oil palm trunk as a timber substitute. So I think we have a couple of questions so far, but if any of you have any question, please type it in the chat box. Dr. Ali Shalbafan, he was asking you that it seems that he was also part of University of Hamburg during his study, and he was asking about more explanation regarding new tools reinforced against silica content, because it seems that the silica has abrasive characteristics that can torn out the cutting tools. So he was asking about this. Are there any new tools that can resist the silica content? And also he was asking regarding silica, how would be the biological durability of these types of products for long time usage?
Okay, yes, thank you. Thank you, Ali, and nice to see you again. Not personally, but okay. The problem, I mentioned this because the ash content up to 3%. This is due not only to the trunk material, but it is even more with the front material, also the empty fruit bunches and the silica content. So this really is a big problem for the normal tools. And this is one of the problems at the moment in processing all palm fibers, because what is done in all the countries which are using all palm fibers, they have no adapted technology. So they use the same machinery as before, the old machinery from tropical timber processing. They use the same saw blades, the same cutter heads and everything. And we did the same at the very beginning, and we found out that, for example, we have to change it with coconut processing. After 2 trunks processed in the sawmill, we have to change saw blade. And with the oil palm, after 5 or 6 trunks. Then we invited one big tool manufacturer, tool producer in Germany, Lights Company. And they developed new tools, especially new tool geometry and new tool materials. And with that, we have an increase of Mr. Kisselbach from Lights is among the participants. He could explain much more. And again, I asked Mr. Kisselbach already to give a presentation in September about this problem, because it's not only due for the trunk processing. It is the same if you produce any fiber material from the fronds. Or Mr. Ali Schreiber-Fahn is producing or is intending to produce particle board from date palm fronds. Then you have the problem in processing the particle boards in the furniture industry, for example. So this new tool materials and the new tool geometry and the new factors in the processing itself makes the difference. And really, they are very big achievements during the last 5 years. So this is one answer. I can't go in detail because we'll do it in September. And the durability, of course, this is a crucial point. As higher the density is, as more durable the wood is. So we have we did have one slide with the durability factors. So low density is not very durable because of the high sugar content. We have up to 8% sugars and starch content. So, and fungi love to eat the sugar. So what we can do is we can use the common preservatives, of course. I mentioned a temporary preservative is like, for example, acetic acid. It helps you a couple of days between sawing and drying, for example, but you can use the more hardcore preservatives as well, as with the softwoods, for example, as well. And there are some other strategies I don't want to talk about in detail at this very moment, where we can even achieve, let's say, even for the low density material, which is nowadays problematic, quite a good natural durability. So we have tests with 1 year in tropical climate without any mold, without any fungi, there's no insect attack, nothing. So Ali, if you're interested more with your date palm fronds, so we can talk bilateral.
Okay.
Thank you.
So Dr. Liu, there's a question from Dr. Adham Al-Sayed. He was asking how thin could be the single layer of the ply, and are the skin layers or the veneers, are they made from oil palm or just the block?
Okay. For the single layer that we can peel using the oil palm, the ideal one is a 3.5 and above, 2.5 mm and above. Because if you peel too thin, this will be difficult during the handling process because it's too soft and also fragile, easy to break if in a big sheet. But the ideal one is if can peel, the thickness is about 3.5 and above, the ideal one. But suitable for the core plywood, if you want to have this for the surface and also for the back, maybe you can peel it really thin, and also if a peel to the thick veneer, you have to compress it for the surface.
Mm-hmm. Okay, thank you so much. I think we need to move on to the next presentation, but if you have any questions to Dr. Liu or Professor Fruehwald or Dr. Katja, please feel free to chat or type any questions in the chat box. Thank you so much for this amazing presentation. It's really very interesting. So the next talk for the coming presentation, we will not talk about oil palm, but rather it will be on coconut palm, and it will be titled Recent Trends in Processing Coconut Palm Oil. It will be presented by Professor Dr. Navin Rastogi, who is the department head of the Food Engineering department at the Central Food for Technological Research Institute in India. Dr. Rastogi, can you please start sharing your screen?
Yes, I'll be talking. My name is Dr. N. Rastogi, and I'll be talking about coconut-based high-end value products. And this is all done based on our research work on the coconut, because India is rich in the coconut palm. And what are the coconut value-added products we have made is that major thing is that, like, we can make a desiccated coconut, and then spray-dried coconut milk powder, and then virgin coconut oil, and the coconut beverage from the coconut. So we have made different products, and these are some of the byproducts also were used in one of the products. If you look at the integrated processing of the coconut, like each and every part of the coconut plant is being used in any of the forms. Actually, basically, I belong to a research institute in India where almost it is comprises of 17 R&D departments, as well as it is the major one of the research institute in the food technology, and where we have used almost all the parts of the coconut. And like if it is, when you take the coconut, we shell the coconut, we get a ball copra, and we can get the shell. Shell can be used in many ways. And then we can take the white endosperm, that white color of the coconut, that can be used for the flakes grating. And then we can, whatever the coconut water comes out, it is mature coconut water or tender coconut water. It has lot of applications. Then we have used, and then we can white endosperm, we can extract the milk, and after extracting the milk, we can extract the virgin coconut oil from the milk, and with coconut cream can be packed, and we can extract even the coconut whey proteins. The different approaches here, the purpose is to, like, here they introduce and adapt. There are new technologies that are developing in the food sectors, and the purpose is to adopt new technologies in the area of the coconut sector here, so that the rural economy becomes vibrant and it becomes a viable economy, and development of technologies for the byproducts in a coconut processing to increase the consumption, because the consumption of the coconut is decreasing. So we want to use to make a different product so that the consumption of the coconut increases, and whatever the byproducts are being wasted, that has to be used in some way as a value-added products. So what are the different technologies? So this is the mainly technologies developed at the CFTRI. It is the CFTRI is a part of the CSIR laboratories network, and here we have made a different technologies. I'll just brief about this. And this is like a desiccated coconut. It's very well known. Like desiccated coconut is a coconut endosperm is grated, and then it is dried and it is used in many dishes like application in the sweet desserts, pastry, chocolates, and other places. So it has a lot of market, and this is the technology available with us. And other thing is the coconut milk. The coconut milk is a product like of the tropical climate and great demand in the industrial culinary. So if you want to use this coconut milk in many of the dishes like fish and other curries and everything, but the problem is that it has to be extracted, and then it is a very cumbersome job to extract the coconut milk and add it to that. Then what we have done, we have extracted the coconut milk and spray dried, and form is available in the market. And even most of the whatever the product is made in India by several companies is being exported, and it can be even used in the flavored milk, milkshakes, rice puddings, savories, and other traditional products like vegetable dishes and other places here. So how this is the product we have made here. How it was made it here, like we as coconut, we took shelling, paring, disintegration, we extract the coconut milk, and that milk has to be formulated because this milk contains around 35% of the fat, and it is not possible to spray dry immediately. So it has to be formulated and then spray dried. And the spray dried product looks like this, which can be added in any of the food products. And then this product contains around 63 to 65% of the fat, and it's still in the form of the powder, a free-flowing powder. And another product what we worked in great demand is the virgin coconut oil. It is the coconut oil which is made by not using any of the heat treatment. Most of the coconut oil extraction, and these people are using the heat treatment and then getting the oil. Here no heat or shear has been used, and this it is at the cold condition the virgin coconut oil was made, and it is rich in the lauric acid and gives a very high value for the maybe different it is health benefits can be derived from the VCO, even like anti-cancer and antioxidant activity. Everything is very high here, and it is a stable. Coconut milk is a stable emulsion. It is very difficult to break the oil and the protein. So there are many people. When we started working on that, even people are not able to break the emulsion and separate the milk. So we achieved the milk, and around 90%, 99% of the milk fat was separated from this, and then we could achieve the virgin coconut oil. The applications are like in the pharmaceutical industry, cosmetic applications, body care, good for seasoning, cooking oil, directly consume. It has a mild sweet aroma, but it has a very high export potential. Like, and it has a very high medicinal value. So maybe there
Seems that we lost the connection.
Yes, I think Dr. Navin has perhaps connection problem. Yeah, so he seems to be online, but
Doctor, no, maybe the network. Just we give 1 minute or 2 minutes because screen is moving. That.
Yes.
Then we will back just. I think it is stuck or something.
So, Dr. Rastogi, are you still connected? I think if there's a problem with the internet connection, you may try to stop your camera. This might help. I think we can see this screen working, but there's a problem with the audio. So I think he was disconnected.
Mm-hmm.
Sorry about this technical problem. Let's see if we can get him back. Okay. So we're sorry about this. We'll just wait one more minute. And if he's still unable to join, perhaps we can proceed with our next scheduled session.
Now he's rejoining. I already admitted him.
Hello?
Yes.
So we can hear you now.
Yeah, just
okay.
continue.
Do you want to start sharing your screen again?
Is that okay? Like, can you see the slides?
No, not yet.
Can you see?
No, it's not showing yet.
Maybe you can again share the screen, you know.
Okay.
Okay.
So if you have a problem with the sharing from your side, I can share from my side. But just try to give it one more try. So I think he was disconnected again, but so we're sorry. He was disconnected again, but now he's back online. Okay, so Dr. Rastogi, can you try to share your screen now? And please unmute yourself.
Maybe can you stop the screen and again share, you know.
Okay, so now it's working.
Yes.
Okay.
Yes.
Can you hear?
Yes.
Okay, so I was just talking about the oil which is made from the coconut, virgin coconut oil. And this technology is transferred to different industries. And most of the produce is being exported because it has a high medicinal value. And this was even received the best technology award. Another is that, like, if we take a 500
Can you
coconuts.
do full screen? Can you do like a presentation mode or full screen?
Yeah. Can you see now?
Yes, thank you so much.
Okay. And this, we just show the material balance. Like if we take the 500 coconuts, it will give us around 30 kg of coconut oil and all other different kinds of the valuable products. And the physicochemical properties, if we look at this, the whatever made by our CF-TRI technology was found to be the best, and refractive index, lauric acid was found to be very high. Vitamin E was very high in this whatever we have made, because we are not subjected to any of the thermal treatment. And this is another product, like wherever the spent product after the extraction of the milk, whatever we get, that is a fiber, and that fiber can be converted into a dietary fiber from the plant sources. And since the color of the coconut is white, this dietary fiber can be added to any of the food product, like it can be added to any of the chocolates or any of the product to be fried, and then like it has to be grind in such a way that it should retain the shape of the fiber, like before grinding and after grinding, we are just showing here. Another technology is the tender coconut beverage. In the beverage, we have made, this is the beverage made from the tender coconut milk here. Tender coconut milk was added with the coconut water. And then when we added this, washing, grading and blend it together, and then formulating, heating, filtering, and then it was filled up, and then again it was heated to 95 degrees, exhausting. It was just like an autoclaving here, and then it resulted in a form of bottled tender coconut beverage, only mainly from the coconut here. And it is a shelf life of around 6 months. And this is a new type of product based on the tender coconuts. Now, nutritional facts and the microanalysis, like we have done, and like that in this case, it was having a product was all these mesophilic and thermophilic bacteria. Their spores were absent, and the fermentation test was negative, and the product was self-stable for around 6 months. And we have done the sensory analysis of the product. We have an attribute was like a whiteness, consistency, coconut-like flavors, and a sweet and overall quality. Product was, it was well received by the product, was acceptable to the customers because we have used the coconut, tender coconut and the tender coconut water put together and made in the form of the beverage. The product was acceptable at around 3 to 6 months. It was at ambient conditions. It was found to be stable at the ambient conditions. And this another thing is that mature coconut water is generally wasted from the industries. So what we have done is mature coconut water, we have concentrated to 60-degree Brix using filtration, centrifugation, the evaporators, and then it is concentrated and then added to the other like a pectin and xanthan solution, and we made it something like a beverage here. And then whatever the coconut fibers were there, that was spread in the coconut. So just to give a taste of the coconut, it was only just to protect, like whatever the product being wasted, it was used here, and it gave a very good shelf life and the taste of the coconut fibers also. So most of the products and whatever we have done, it is all patented, Indian patent. Another characteristics of the spread we have just shown, the Brix was around 68, acidity was there, color and flavor, everything was estimated here. And this is the quantitative descriptive analysis, like product was well received by the people here. And then attributes the number, consistency, suspended solid, honey-like characteristic coconut, and product was well received by the panel and scored high scored at 12. And this is also patented in India. The membrane processing of coconut whey protein, what we have done, this is the one of the vegetable, very good source of the protein, because there are very few vegetable source of protein here. So when we extract this coconut milk, we get lot of vegetable, a lot of protein, because we need to separate the protein from the fat, and then we get oil. So whatever is the protein separated, that also finds a good market in that. So how we have done it, like we did with the ultrafiltration, and the retentate is having 98%, that was spray dried and can be used as a spray dried protein powder in different formulations, because again it is a white color and very high value protein. So another this experiment in the product is like tender coconut water concentrate. Most of the time, if we use the reverse osmosis, we can concentrate up to 30-degree Brix. So in the new process, like a forward osmosis or osmotic membrane distillation, what we can do is we can circulate the coconut water from one side, and then it comes back here, and other place it is the concentrated salt solution is circulating. So what is happening here is water goes from the coconut water to the salt solution, where coconut water get concentrated and salt solution get diluted. Here the coconut water can be concentrated up to 60-degree Brix. And when it is concentrated to 60-degree Brix, it can be kept as such are maybe added with some sugar, little bit of sugars in those, and it can be reconstituted as and when desired. And because the amount or the volume was reduced so much, it can be transported anywhere. This is the process osmotic membrane distillation and reverse forward osmosis. The same way like that, if you circulate this, water will go from the coconut, it will go to the concentrated salt solution, and then the coconut water will get concentrated. When it gets concentrated, then we'll have a very highly concentrated coconut water around 60-degree Brix, and then we can dilute it and use whenever we want it. So this is just about the how it works about this here. This is the, suppose this is a water flux going like that. If it is, this is a concentrated solution here, and water will go here, and then this coconut will get concentrated, and water will go to the draw solution where it gets diluted. So this is end of my presentation. I'd like to thank the CFPRI organizers for giving me this opportunity, and thanks for your attention. Thank you very much.
Thank you so much, Professor Rastogi, for this excellent presentation. I think it's a whole world of opportunities with using coconut byproducts as well as extracts from the coconut itself. So if you have any question to Professor Rastogi, please feel free to type it in. Okay, so I have one question. Perhaps I don't have like a background in food engineering, but I would like to ask if there are any, I mean, you see any similarity between the work being done on coconut with respect to other type of palm products? Like, could this be something that can be similarly applied to, let's say, dates or oil, fruit?
Oil, at the moment we are not working on the we are working on the other vegetables oils, the refining, deacidification, and desolvent. Actually, we are trying to use membrane processing for the deacidification or degumming and desolventization of the oil using the membranes. Maybe this work is at a infancy. When it comes maybe by September or something, if we collect some more data, we will be able to present some work how the oil, membranes can be used for the desolventization and degumming of the oils. So this work is ongoing at the moment.
Okay, so this sounds very good. So anyone else has any question? So we will have like about 5 minutes break, and we will come back for another session by Professor Dr. Aidah Jumahat. So stay tuned, don't go anywhere. We'll just like break for 5 minutes if anyone wants to like answer the phone or reply to a text message.
Okay, thank you.
Okay. So welcome back, everyone. So I hope this was a refreshing short break. So I just wanted to acknowledge the attendance of two great figures in the area of bio-based materials and biocomposites, Professor Hamid al-Mosli, despite that he wasn't able to provide the welcome address, but he was able to join us. Also, I recognize the attendance of Professor Walter Lisi, who is considered like the founding father of or the father of bamboo. I know he is the professor of Professor Arno Fruehwald. So now we have a new session, and this time it will be on the sugar palm. The title is The Mechanical Properties of Treated Sugar Palm, Arenga Pinnata Fiber and its Composites. And it will be presented by Professor Dr. Aidah Jumahat from the University Technology Mara. Professor Aidah, I think, okay, you already started the presentation. So the floor is yours. So
okay, thank you, Dr. Midani, for the introduction. Assalamualaikum and very good afternoon, all speakers, all professors, doctors, researchers, yeah, and all participants for today. My name is Aidah Jumahat. I am the Associate Professor of the Faculty of Mechanical Engineering, University Technology Mara. At the moment, I'm attached to the Office of Deputy Vice Chancellor, Research and Innovation as the Deputy Director of the Industrial Technology Research Niche Area. Okay, so my presentation today is related to Arenga Pinnata Fiber, reinforced polymer composite. I'm using epoxy. So here I'm concentrating on mechanical properties. I'm just maybe I will share preliminary results on the tensile and also flexural properties, and also what will be the effect of Arenga Pinnata if we treat with silane, and also what will be the effect of nanosilica. Yeah, if we put into the Arenga Pinnata fiber reinforced polymer composite, denoted by APREC. Okay. So this is a little bit about my research background, yeah, my research areas, and basically my research areas on the fiber reinforced polymer composites. Before this, I'm only concentrating on synthetic fiber, yeah, mostly carbon fiber and also glass fiber. Now now I move towards the natural fiber, and before this I'm doing Knaf, and now I'm concentrating on Arenga Pinnata fiber. Okay, so I'm really interested in predicting, yeah, actually in predicting the strength, yeah, compressive strength, tensile strength, yeah, flexural strength of natural fiber composites using several techniques. Okay, so basically I'm using fiber micro buckling model, yeah, to predict the compressive strength, and I'm using various types of software, especially ANSYS, in order to predict tensile strength, flexural strength, and others. Okay, so UITM at a glance. This is about UITM. Only a few minutes, yeah. UITM is situated near to Kuala Lumpur, and also near to Putrajaya. Okay, as everybody know, yeah, neighboring country for Malaysia is Thailand, Brunei, Indonesia. Yeah, okay. So here is UITM. Yeah, okay. So UITM is the biggest university in Malaysia, where it has 35 total campuses all over Malaysia. Okay, it has one main campus where I'm working in is at Shah Alam. Yeah, main campus at Shah Alam, Selangor, near to Kuala Lumpur, near to Putrajaya, and the other 13 states all have UITM campuses. and additional 21 satellite campuses. So in total, it's about 35 total campuses, yeah, in UIT in Malaysia. Yeah, UiTM in Malaysia. Okay, so because of UiTM is the biggest university in Malaysia, UiTM has about more than 17,000 staff, academics and support staff, and 526 academic programs, total enrollment about 180,000, more than 180,000 per year. Okay, and also in enrollment total 180,000. Okay, and total graduate, more than 840,000 at the moment. Okay, and UiTM has 31 faculties and academic centers. Okay, these faculties and academic centers can be divided into 4 main areas: science and technology, business and management, social science and humanities, and academic centers, while I'm at the mechanical engineering faculties. Okay, faculty. Okay, and research at UiTM can be divided into 6 niche area where I'm concentrating on the industrial technology. Okay, and UiTM also has 10 research institutes. Okay, 10 research institute. So many areas here, from accounting to transport, to manufacturing and so on. Okay, so basically, what I'm sharing today is about the Arenga pinnata. Common names for Arenga pinnata. It also called sugar palm. Yeah, sugar palm, Arenga palm. Yeah, black sugar palm, kaung palm, ijo. Yeah, gomuti, usually in Indonesia it is called ijo or gomuti palm in India, and kabong or Malaysia we call kabong because this kind of plant producing fruit we call as kabong fruit, yeah, which is very, very delicious. Okay. Okay, so this is how the fiber look like. Yeah, it is in the loose form. It is look like this, and this is in the form of rope. So this is for future application. Yeah. Okay. And the scope of discussion. Midani, can you see my cursor? Midani, do you see my cursor?
Yes, I can see your screen.
Yeah.
Yes.
You can see the screen. Can you see the cursor? My cursor?
Yes,
okay, thank you.
Yes.
Thank you, because I'm referring to my cursor. I don't know whether you can see my cursor or not. Okay, so the scope of discussion for today is about the Arenga pinnata fiber, and here this Arenga pinnata fiber we prepare in the form of unidirectional 0 degree, with certain fiber volume fraction. The effect of fiber volume fraction will be discussed later, and the polymer type is epoxy. The filler will be nanosilica. The functionalization of surface functionalization of the Arenga pinnata is silent, and the mechanical testing, it contains tensile, compression, bending, and others. But for today, I would like to concentrate on tensile and also bending result. Yeah. And this is the overall project about the Arenga pinnata. Yeah, about this project, we collecting the data of the Arenga fiber itself, the properties of a single fiber, and also the properties of the epoxy that we use. And then here it is very important, for us to collect all properties related to 0 degree direction fiber, in epoxy polymer, and also 90 degree properties, under tensile, compressive, or bending type of loading. Okay, and all this data actually we will use for the prediction of tensile, compressive strength, bending strength, and other properties of various types of laminate. Yeah, we will do fiber microbuckling model, and also we specifically use ANSYS, ANSYS modeling, in order for us to predict all the values for strength. Okay, and then the data on the prediction, on the mechanical properties will be presented, inshallah, during the Bipalma conference this September. Okay, so hopefully everybody will join the Bipalma conference this September. Okay, So presentation outline, so in general about introduction to natural fibers, okay, matrix selection, problem solution, objective, significant, yeah, experiment, result, discussion, yeah, and also conclusion. So basically about the classification of the natural fiber. These have been most of the fibers here, like oil palm, coconut palm, yeah, have been discussed by the previous presenter. Okay, and I'm concentrating on Arenga Pinnata fiber. Okay, actually this fiber, okay, it is not inside the trunk, it is around the trunk. Okay, so when compared to coir, oil palm, and so on, this Arenga fiber, we obtain the fiber outside the trunk. Yeah, it is around the trunk. Okay, so in general, natural fiber composite, why it is being used nowadays? Because it is used to replace the synthetic fibers, especially carbon and also glass. Okay, and this is due to the environment concern, financial, and so on. And the advantages of the fiber, the advantages of this natural fiber, it has a good specific strength, yeah, specific strength and specific stiffness when we compare the stiffness to its throw, yeah, and also strength to the density, yeah, it is very good. Okay, because natural fiber is very light, yeah, in weight. Okay, and then it is a renewable resources, low cost, and others. Okay, but it has this kind of natural fiber composite has various challenges, especially lower strength, lower durability. That's why we try to improve the properties of this natural fiber composite by doing the surface functionalization, by adding nanoparticles and so on. So all those are techniques in order to improve the properties of the natural fiber and also to overcome all the challenges because of the weakness of this natural fiber. Okay, there are so many applications at the moment for natural fiber. Yeah. This has been discussed by previous presenters. Okay, so basically, this is the plant. Yeah, this is the Arenga plant. Okay, it's about it can be up to 20 meter tall. Yeah, with a straight trunk that can be 32 centimeter diameter. Okay, one of the plant that produces black color fiber. Yeah, all around its trunk. So from here we get the Arenga Pinnata fiber. Okay, so it is planted, yeah, by British East India Company, yeah, in Penang. It was in year 1800, yeah, and the usage for this type of plant. Okay, it is not only we can extract the fiber, yeah, the fiber, the palm also, yeah, can be used. Yeah, the palm sap can be used as palm nira, yeah, fresh juice. The trunk can be used for starch, for biopolymer. The fruit used as dessert, yeah. This is what we call as the buah kabung just now, and the leaf, yeah, can be used as well. So we use here in this research, we're concentrating on the fiber that we call the Arenga fiber or ijo. Yeah, the best properties of this kind of material when compared to the other kind of natural fiber is this fiber. Yeah, it is well known as a seawater resistant fiber. Okay, so it is used for seawater application. Yeah. Okay, it is also can be as rope, roof, broom, yeah, and also can be substitute for geotextile fiberglass reinforcement, yeah, underwater or underground cable. Okay, but of course, extensive research. I'm doing extensive research on this. Okay, so the result that is presented here is the preliminary result, yeah, of the effect of unidirectional fiber on unidirectional Arenga fiber on the mechanical properties of the composite. Okay, so this is the advantages of the Arenga fiber. Yeah, easy to extract the fiber, hydrophility, and resistant to seawater. Okay. So the conventional use as rope, broom, and so on. Okay, and the current potential will expand the usage, yeah, for bridge, pathway, yeah, for drain cover, yes, sewer drain cover, and also any types of seawater on top, or we can use for seawater structures. Okay. Okay, the material selection, we use epoxy resin. Yeah, we use epoxy resin. Okay, and everybody know that epoxy resin has a brittle properties. Okay, due to very high cross-linking. Therefore, we modify the epoxy with nanosilica in order to increase the stiffness, the strength, and the toughness. And also, we use the Arenga Pinnata fiber. Okay, so in order to improve the Arenga Pinnata fiber, we treat using silane. Yeah, and also we align it in unidirectional because we would like to know the basic properties of this kind of fiber in order for us to predict, yeah, the properties of the in order for us to predict the properties of the laminate. Yeah, if we prepare a structure, yeah, based on layup or laminate, so we have to predict what will be the properties of this laminate. So therefore we have to have like a very basic data on the tensile strength, yeah, on the transverse strength, and also on the shear strength. These three properties are very basic, yeah, in order for us to do the prediction. Okay, to do the strength prediction. Okay, so here for today, the objective of the presentation today, I would like to share what will be the effect of fiber content, Arenga fiber content, and also nanosilica in epoxymetry. Okay, in order for us to prepare the composite, and also what will be the mechanical properties. Here we will concentrate on the tensile and also flexural, and also what will be the effect of silane treatment, yeah, on the fiber to the strength, to the tensile strength or flexural strength of the composite. Okay. So the significance of a study, okay, the significance here for the study, we use the natural fiber, and we try to improve the metric by adding the nanosilica. We widen the application of Arenga Pinnata from traditional use, okay, to making structures. Okay, and these structures as well can be used for seawater application. And other than that, we are observing the effect of silica, yeah, in this study. Okay, and the experimental work, the material Arenga Pinnata were obtained here from Kuala Pilah, Malaysia, from Negeri Sembilan, and epoxy resin used is Miracas, GBA, nanosilica from Nanopop F400. The maximum nanosilica content in the epoxy is about 25%. It's about 40%, but if we dilute into the epoxy, it's about 25%. Okay, and we use silane solution in order for doing the treatment of the surface of the Arenga Pinnata. And we did density test, hardness test, and also we look into we observe under SEM the fracture surface or the microstructure of the fiber. And also we did flexural test, tensile test. Actually we did a few other tests, yeah, but here we just concentrating on these two types of testing only. And the material just now, this is the Arenga Pinnata before treatment, and this is the nanosilica. Okay, this is the epoxy, and this is silane, and these are all the test machine used, yeah, for the study. Okay, actually the study were conducted on various types of testing, but for today we just concentrating on a few example of results. Yeah, and here is the result. Yeah, we're concentrating on three different things: effect of fiber volume fraction, yeah, on the mechanical properties; effect on nanosilica on the mechanical properties, here both for polymer itself and also for the unidirectional Arenga Pinnata composite; and effect of the surface treatment, yeah, of the Arenga Pinnata on the mechanical properties. Okay, so this is the density. This is the density result. Okay, as we can see, the density of the polymer. Okay, as we can see, the pure polymer here, the value at right hand side is the value is about 1.114. Yeah, it's about 1.14. Okay, the density gram per centimeter cube. Okay, and if we put nanosilica, yeah, from 5 to 25 weight%, okay, the density slightly increased because of the density of the nanosilica is higher than the polymer. Yes, so therefore it the density increase a little bit, yeah, from 1.1 up to 1.26 gram per centimeter cube. And if we put Arenga Pinnata fiber in the polymer, okay, in the polymer of 10 volume%, yeah, 10, 15, 20, and 25. Okay, so we can see the density of composite. APREC is the composite, Arenga Pinnata reinforced epoxy composite. So the density of the composite, of course, yeah, it is lower, yeah, than the epoxy with nanoparticles. Okay, so with 10 volume%, yeah, Arenga Pinnata, the density is about 1.13, and if we increase to 25, it's about also 1.13. Okay, this is because Arenga Pinnata fiber is very light. Yeah, okay. If we put 10 volume%, this is random. Yeah, random orientation. Yeah, 10 weight% random orientation, and if we put unidirectional, about 10%, of course the value of density almost similar. And if we put the 5% of nanosilica in 25 volume%, yeah, 25 volume% Arenga Pinnata fiber, yeah, the density is about 1.15 gram per centimeter cube. Okay, so increase the nanosilica, of course the value of density increases. Okay, with the treatment, TAPREC mean surface treated Arenga Pinnata fiber. Okay, we surface treated of 25 weight%. 25 volume%, sorry, 25 volume% Arenga Pinnata fiber, the Arenga Pinnata fiber, the density, of course, it is similar. Yeah, it is almost similar to the untreated fiber. Okay, so effect of fiber volume fraction. Effect of fiber volume fraction on flexural. We concentrate on flexural and tensile properties, yeah, of the composite. As we can see here, when we compare to the pure epoxy polymer, the modulus is about 2.88. If we put Arenga Pinnata, yeah, Arenga Pinnata in the epoxy, the modulus increases from 3.7 or 3.8 to 3. Almost 4, yeah, almost 4 GPa, yeah, with 25 volume%. yeah, 25 volume percent unidirectional Arenga pinnata. In the epoxy, the modulus increases from 2.8, yeah, 2.88 to 3.98. Okay, so this is the value of the modulus, and this is the value of the flexural strength. This is under flexural test, yeah, for flexural test. Okay, so flexural strength for pure polymer, for pure epoxy is about 61 megapascal. With the addition of unidirectional Arenga pinnata, the strength is slightly improved. Okay, so this is the result of the flexural strength of the composite, Arenga pinnata composite. Okay, as we can see here, this is the failure mechanism involved. It's involumetric cracking, and also some of the fibers it is being pulled out. Okay, during bending test. Okay, and then this is under tensile, yeah, under tensile arrangement. So the tensile strength, yeah, the tensile strength of this Arenga pinnata composite, yeah, when compared to pure epoxy. Okay, so as we can see, the tensile strength for pure epoxy is about 53 MPa. Yeah, it increases to 68 MPa for tensile strength. Okay, when we add 25 volume percent of Arenga pinnata in tested in unidirection. Okay, the modulus, yeah, without any fibers is about 1.43. Yeah, the modulus, and it increases to 4 gigapascal if we put like 25 volume percent of Arenga pinnata. Okay, so this is the friction mechanism. Yeah, it's involved only a little bit debonding here, and also fiber pull out. Yeah, can be seen. Okay, so okay, and then what will be the effect of the nanosilica? Yeah, nanosilica
Dr. Aidah,
yeah?
Can you try to wrap up in maximum 5 minutes?
Okay, so I will wrap up.
Have time for Q&A.
Okay, so I will wrap up. Yeah, we can see almost similar results. Yeah, for adding the nanoparticle, as we can see the increase in flexural modulus, and also flexural modulus of the polymer itself, and flexural modulus increases, yeah, for the composite, Arenga pinnata composite. Okay, and this is intention, yeah, intention. Yeah, the Young modulus increases from 1.4 to 1.87. Yeah, this is for epoxy. If we add up to 25%, nanosilica. For the composite, yeah, for the composite, the best formulation, as we can see here, yeah, this is for 25 volume percent. Yeah, this is with the addition of 5% nanosilica, it increases the properties of the tensile modulus increases from 4 to 4.1 GPa. Okay, so if we increase the nanosilica content, we can see that the tensile modulus become lower. Yeah, this is due to wetting, yeah, wetting problem in the resin system. Okay, so that means the best formulation that we can have for this kind of composite is about 5% nanosilica in 25 volume percent unidirectional Arenga pinnata fiber. Okay, so okay, so other than that, the effect of surface treatment, actually for the surface treatment, we can see a slight increase. Yes, slight increase. If we treat the surface of the Arenga pinnata fiber using silane, actually it will improve the properties of the composite. Okay, and so this is for future experimental work. Okay, other than the mechanical test, moisture absorption test, yeah, we will do modeling and simulation as well. Okay, so with that, thank you very much. Back to you, Dr. Midani.
Okay, Thank you so much, Dr. Aidah, for this excellent presentation. If any of you have any questions to Dr. Aidah, please type it in the chat box. I have a question. I hope you can have an answer for it. But you mentioned that one of the unique characteristics of the Arenga Pinnata fiber is that it has a high sea salt or a high seawater resistance. Is this correct?
Yes, yes.
Okay.
That is the what we call that is the benefit or the best about this kind of natural fiber when compared to the other type of fiber. So it has a very good it has a very good resistance to moisture, and it has a very good resistance to seawater, or if metal we said it is corrosion resistant, but this is natural fiber and this is polymer, so it is very good in terms of resistance to acidic or alkaline material.
Okay. This is really a good feature. I know that there's only one other natural fiber that has such characteristic, which is abaca, or also known as the Manila hemp. So I don't know what makes a fiber. What are the, like, is it something in the microstructure that makes this fiber has this special resistance to seawater?
Dr. Midani, actually at the moment we are still doing the testing on the seawater, and inshallah we will present it during in September.
Okay.
The characteristic.
Sounds good. Okay, so I think we don't have any question. So so now it's thank you so much, Professor Aidah. So
welcome.
So let me proceed to the final presentation, which I will be doing. Just give me a second. So I will go ahead and share my screen. So Dr. Jawaid, can you see the screen?
Yes, Midani, the screen is clear to us.
Okay, thank you. I know it's becoming late, especially for our colleagues in Malaysia and other parts of Southeast Asia, especially who are having iftar coming up in less than 30 minutes, I guess. So I hope you still have a few minutes to attend the last presentation. As I mentioned earlier, my name is Dr. Mohammad Midani. I'm an assistant professor at the Materials Engineering Department at the German University in Cairo, and I'm also an adjunct assistant professor at the College of Textiles, North Carolina State University, and the managing partner of Intexive Consulting. So as most of you know, that the entire world is currently struggling with plastic pollution, but unfortunately, plastic is not just like plastic bags and wrappers, but they actually dominate our everyday textiles and fibers. So if you think about like only one type of plastic-based fiber, such as polyester, you will see that it has grown from 5 million tons in the 80s up to more than 50 million tons nowadays, exceeding more than 50% of the world consumption of textile fibers. But the question here is, I mean, what did people do before having those man-made fibers? So actually, they used to rely completely on natural fibers. But what happened is that with the growing populations, with the increase in the number of population, with the improvement in the living standards, and the increasing demand of like textile fibers. Unfortunately, on the other hand, this increase in demand wasn't actually associated with increase in supply for natural fiber. And this is due to the limited resources that we rely on for our natural fibers, whether these are from live animals or from fiber crops. So the key word here, or the problem that we're facing, is lack of biodiversity in natural fiber sources. And with the ongoing interest in natural fibers, I think there is a high need for increasing this biodiversity. And as most of you know, that natural fibers can be classified either to vegetable fibers, and these are the fibers obtained from plant resources, as well as animal fibers that are obtained from live animals. And those vegetable fibers are actually superior in properties, but unfortunately, they have been forgotten in the modern context. But nowadays, there is an increasing interest, and leading companies around the world are currently pushing the limit in rediscovering those natural fibers in applications with higher added value and more commercial applications. This is why we will find that if we look at the world consumption of the vegetable fibers, excluding cotton, over the past 10 years, we will find that it has been growing steadily with a compound annual growth rate about 4.2%, and it has reached almost $4.7 billion in 2019. But unfortunately, this increase in value hasn't been associated with increase in production quantity. So this increase is actually limited to increase in the unit value, or the price of the fiber. And the reason is because we completely rely on very few fibers to obtain our vegetable fibers. So this is what I call lack in biodiversity of fiber crops. So if we look at, okay, just a minute. So if we look at the world production of vegetable fibers, excluding cotton, in 2018, we will find that more than 80% of our fibers were obtained only from 3 crops, and this is jute, coir, and flax. As well as if we look at the fibers obtained, more than 80% of the fibers obtained from only 4 countries, and these are India, Bangladesh, France, and Vietnam. So this is why in 2010, the Food and Agriculture Organization of the United Nations, they started an initiative called the Future Fiber Initiative, and it was the purpose, or the goal of such initiative was to revive those old forgotten fibers, such as the abaca, the sisal, the coir, the jute. But unfortunately, it was still focused on those very few fiber crops. So we asked ourselves, are there other sources? I think the screen, okay. So we asked ourselves, are there other sources of fibers or other sources from which we can obtain vegetable fibers? And the first thing that came to our mind was the date palm byproducts, because I mean, date palm is one of the major elements of flora in the Middle East and in North Africa. And we know well that it is a rich source of cellulose fibers. And as most of you know, there are more than 140 million date palms around the world. that are, as I said, concentrated in the Middle East and North Africa. And those 140 million date palms, they generate more than 4.8 million tons byproducts of pruning, whether it's in the form of fruit stalks or front stalks or leaflets or the coir that surrounds the trunk, or even in the form, or even the trunk itself at the end of the palm life. And those byproducts in the past were actually used in every aspect of living. They were used in fencing, roofing, making furniture, making crates, making mats, ropes, literally every aspect of living. And there were entire villages who were specialized in making those crafts. But unfortunately, with the widespread of plastic and other synthetic materials, they just took over those, I would say, traditional crafts, and the entire economies that were based on making those products just collapsed. So unfortunately, these byproducts turned from being a resource into becoming a burden on the environment and on the palm growers. At the end of the day, they have to get rid of them. So they became one of the major causes of fire accidents due to the inappropriate open field burning of those byproducts. So we saw a very good opportunity here to redirect those agriculture waste from the waste stream to the value stream. And we were able to extract the first textile fibers from the byproducts of date palm, and we call it palm fill. Excuse me. And we were able to convert it into different textile forms, including hackled tows for spinning, including spun yarn, including chopped fibers, and then could be converted into non-woven mats or woven fabrics, or even blended with a matrix and pressed into a natural fiber composite panel. And actually, palm fill fiber has a set of unique features and benefits. It's not only sustainable, but it's also 100% biodegradable. It's also, it doesn't compete with food production. It doesn't cause deforestation. And also it has a very low carbon dioxide footprint. Actually, a single date palm has the ability to absorb more than 200 kilograms of carbon dioxide every year. It's also an abundant, as I mentioned, it's already available in countries with very high concentrations of date palms, such as Saudi Arabia, the Emirates, Iraq, Iran, Egypt, Algeria, and many other countries in the region. And also it's economical in manufacturing. After all, the value or the price of the byproducts are equal to zero inside the field, and it doesn't require any extra investment in land, in water, in fertilizer, or anything else. And also the fiber is a high performance fiber. It has specific tensile properties, 5 times higher than structural steel. It has very good acoustical and thermal insulation properties, even higher than carbon fiber and glass fiber. And it's also lightweight and safe. It's only 50% of the weight of glass fiber, and it doesn't require any special personal protective equipment when we're dealing with it. And most importantly, it's compatible with the existing production system for textile processing system for other vegetable fibers, and it can easily be blended with other vegetable fibers. So I will just quickly go through some of the potential applications of such fiber. So due to this unique properties and characteristics, it represents a sustainable material base for a wide spectrum of industries. This includes natural fiber composite panels in the automotive, such as door panels, door panels, trunk liners, seat backs, parcel shelves, and several other components that are nowadays an integral part of modern day vehicles. Also, some of the well-established applications in construction and building, such as plaster reinforcement, also in making area rugs, also in using it as a carpet backing. This is a very big market that is dominated by jute fiber. Also, another interesting application is thermal and acoustical insulation bats. And this is also one of the emerging applications. Another application that is considered the traditional one is in packaging, in making burlap sacks and Haitian fabrics. But also, on the other hand, there are other type of modern packaging, like in making biodegradable cutlery, like the ones that Professor Jawaid have shown us. And this, I think, is a very important application, especially with the wide ban of single-use plastic. And currently, we're seeing the single-use plastic directive of the European Union. Another application is freezing. Okay, the screen is freezing. Okay, now it's working. Okay, so another application is with non-wood paper. So this is also making paper from sources that didn't require cutting trees, and it's becoming one of the important topics in the wood, in the paper making industry, whether in making decorative paper or in making tobacco paper or in making banknote papers. And finally, some of the traditional applications like making ropes and twines, or even making sporting goods from natural fiber composites. Okay, so the question here is, how is it made? So actually, palm fill fiber, it is based on a proprietary technology for extracting long, fine, pure, and flexible fibers from the byproducts of the date palm, such as the front stalks and the fruit stalks. But there were actually several challenges associated with extracting those fibers. And as you know, that every part of the date palm, or all types of byproducts of date palm, can be used for extracting cellulosic fibers, whether these are the front stalks, the leaflets, the fruit stalks, or the quar that surrounds the trunk, or even the trunk at the end of the palm life. But in order to be able to extract fibers from these byproducts, it's very important to have a very good understanding of the morphological anatomy of each fiber inside those sources. So for instance, if we look at the morphology of the quar, you will find it has more like a honeycomb cross section. If we look at the front stalks, we will find that it's made of fiber vascular bundles that contains large hollow lumens. If we look at the fibers from the fruit stalks, they are more of like pure fiber bundles. So if we take the front stalk for an example, if we look at the cross section of the front stalk, we will find that it's composed of, as I said, vascular bundles, or let's just call it tubular fibers. And these tubular fibers are more like, pipelines that are intended to transport the moisture and other nutrients to the different parts of the front. But around or surrounding the wall of these tubular fibers, there are fine microfibrils, but unfortunately, those microfibrils and the tubular fibers are glued together and glued with other tubular fibers inside the front stalk with a natural glue like the lignin and the hemicellulose. And as you can see here, there are still some traces of this natural glue. So the purpose here was to eliminate those or this natural glue, and also to eliminate the void content and split the tubular fiber into longitudinal segments, because this tubular structure, it provides very high rigidity to the fiber, so you cannot twist it or you cannot bend it, it will just break. So this is why we need to split the fiber into longitudinal segments, and afterwards to continue to fibrillate those fibers into the elemental microfibrils, but most importantly, without causing any damage or breakage to those fibrils. And actually, palm fill technology contributes to the circular bioeconomy, following a closed loop cycle from cradle to cradle. And we have done like a comprehensive research on optimizing the extraction process, and also on characterizing the new fiber and benchmarking it against other high performance vegetable fibers, such as sisal, such as the jute, the flax, and the hemp. And as I always like to say, it's not intended to compete with other natural fibers, but it's intended to complement the offering of the natural fibers. So if we look, I will not get into too much details of this table, but if we look at the properties of palm fill fiber, we will find that it is close to other vegetable fiber. And we strongly believe that this is very promising results, and any future research and investment in such area will result in further refinement to the properties and further improvement to the fibers. So in other words, it's not the end, it's actually just the beginning. So we have published the results of our research in several journals, and it was very well received by the scientific community. We've published an article at Industrial Crops and Products with our co-author, Professor Dr. Ramzi Kiari. And we also published another article in Cellulose by Springer. And last December, we had the chance also to publish the first book on date palm fiber and its composites. And it's now available on Springer online and also on Amazon. So it's still a long journey until we fulfill our our dream to scale up and commercialize these new fibers. So we've been working on this for like almost 5 years now. We came a long journey, passing by the proof of concept and then the prototype development. And then we're currently in the pilot stage, and we're looking for sponsors and partners to help us in scaling up and commercializing this technology. So I will just quickly play a video from one of our semi-industrial trials. It was actually like a spinning trial that was performed on an industrial scale spinning line for flax. So I hope the video played well. Sometimes it breaks due to the internet speed. And we've recently prepared a full development and investment or business plan for anyone who is interested in sponsoring this project. I can share with you the documents if you need it, but I will just skip this for the time being. And from day one of our research, we've been very keen in disseminating our research results. In 2018, we've co-organized the first World Conference on Biopalma to show our new fiber, and and last summer we have did like a commercial announcement about palm fill, and it was featured in more than 35 media articles from leading media, specialized media magazines in more than 14 languages from more than 15 countries. And these include the International Fiber Journal, JEC Composites magazine, Composites World, also from Textiles World, and many others. And also last summer, we prepared the website to showcase the possibilities of this new class of fiber. It's palmfill.com. And you can also, when you visit, you can download the brochure for palm fill. And recently, we've been able to add this new fiber to the material library, the International Materials Library, such as the Brain of Materials in Germany, as well as the Material Connection Library in New York. And it received the seal of material excellence from Material Connection. So as I've explained, we're currently looking for industrial partners to help with the application development. And we're also looking for sponsors and investors to support in scaling up and further commercializing this technology. Okay, and this is just a brief overview on the research team. In addition to myself, there's Professor Dr. Ahmed Hassanain, my partner at Intexiv, and he's also an associate professor of textiles engineering at Alexandria University, and also Dr. Tamer Hamouda, my partner at Intexiv. He's an associate professor at the Textiles Division at the National Research Center of Egypt, as well as Lobna El-Saifi, who is a lecturer assistant and PhD student at the Materials Engineering Department at the German University in Cairo. So just to conclude, I would like to say that investing in palm fill technology is actually investing in an innovation that benefits the economy, the society, as well as the environment. It's investing in innovation or investing in scaling up and commercializing new technologies, investing in creating value from our agriculture waste and redirecting these waste from the waste stream into the value stream. Also investing in exploring new sources of natural fibers and increasing the biodiversity of fiber crops. Also investing in providing green, sustainable raw materials to the industry to help them shift back to natural fibers and green materials, and also investing in supporting the sustainable development of rural communities by building circular bioeconomies within those rural communities that help in improving livelihoods. And this is all based on their local resources. And finally, investing in preserving the local cultures and the technical heritage of our local communities. So with that being said, I would like to conclude, and I would like to thank you so much for your attention. Before I start taking the questions, I will just proceed to the invitation and the concluding remarks and invite you to our upcoming version of Biopalma conference, which will be held online in September from 28 to 30 September this year. If you want to learn more about BiPalma conference, please visit bipalma.com. The conference is chaired by Professor Mohammad Jawaid from the University of Putra, Malaysia. These are just some of the topics of the conference. So the conference is open to any kind of palms, any kind of byproducts of those palms, in any kind of applications, whether in making composites, furniture, pulp and paper, silage, geomats and textiles, wood panels, sustainable energy and biofuel, crafts, like cosmetics, pharmaceuticals. So you just name it. So thank you so much. And I hope I didn't exceed my time limit.
No, Dr. Midani, you finish on time. So now there is no question in the chat box. If any question, please ask the question that or write in the chat box. So Dr. Midani, wonderful talk from your sides on the palm field. And we look forward that I'm one of the, maybe your collaborator in the futures, looking forward.
Sure, sure. So thank you so much, everyone, for attending. So let's see if we have a question here. We have around 260,000 hectares of date palm in Iran. I'm already working on R&D projects regarding utilizing of palm fronds for particle board. Yes, so I think that Iran is by far the largest, has the largest population of date palm. I know this might contradict some of the local statistics, but I think this is the accurate statistic. So if you have any questions, you can email me. I will type my email here, okay? So we need to conclude because people they have to leave for iftar, especially if they are part of preparing the iftar. So thank you again for your participation and active engagement throughout the entire workshop. I know it has been like a long 3 hours, but I personally felt that it was really short time. I enjoyed every presentation. Thank you so much to all our speakers for their dedication and for taking the time to join us, and also to our all our participants, valuable participants. And we wish that you will be able to join us again in September in BiPalma 2021. Thank you again and take care. Assalamu alaikum.
Okay, thank you so much. Thank you so much. Take care and look forward in the BiPalma to all of you.
Thank you. Bye-bye.
And all the speakers.
Thank you.